Let's do another example of integration by parts. Now, in this example, we have the antiderivative of x times the square root of x plus 3 with respect to x. And if we're trying to follow the LIATE guideline for how to choose u, here they're both algebraic. So the question could be, well, which one do I pick? And of course, you could try both and see which one seems to come out easier. But another guideline, sorry, got caught off in the packet, is we normally choose u to be the part that's the easiest part to take the derivative. Because like if we're really paying attention to the formula, after applying the integral of u to v, we're going to get u times v minus integral of v to u. So essentially we want v to be relatively easy to integrate, and we want du to be as simple as possible as well. It's like whatever makes that combination the easiest. We typically don't want du to be too terrible. And again, we want v to be pretty easy to do as well. And in this particular case, my inclination would be to set u to be x and dv to be the square root of x plus 3, because du would just give me directly dx, and then the integral of v should be pretty easy to do. So if I can ever choose u to be just x alone, that is always going to be quite nice. So let's give it a try. So we'll let u be equal to x, which would of course make du be equal to dx. And then we're going to let dv be everything else. So that would be the square root of x plus 3 times dx. And remember, you always want to make your entire integrand, including the differential, part of your u and dv, because we have to match the formula exactly in order to get this to work properly. And as usual, we need to find the integral of v, or dv, to find v. And since this is the same as x plus 3 to the 1/2 power, we could use the power rule, which would be, we'd add 1 and drop the reciprocal. So adding 1 to 1/2 would be x plus 3 to the 3/2, and dropping the reciprocal would give me 2/3. And also, since you might want to be careful about using u substitution here, but since it's just x plus 3, if we were to do a u sub, technically you can do an individual u sub with integration by parts, but you want to be careful because notice I've already used u, and it's probably bad to use u a second time if I'm trying to calculate an integral such as this. But nonetheless, we should be good to go in this particular case. So again, we have integral u dv, and that must be equal to u times v. So we have x times 2/3 x plus 3 to the 3/2 power, and then it'd be minus integral v du. And notice I do have v once again, so ideally we don't have to deal with v that many times, but since this is also relatively easy to integrate by power rule, and since du is just dx, this is just a direct antiderivative, again using the power rule. And this part over here has already been integrated. So once again, we'd have 2/3 x, and then this, we could write this as the square root of x plus 3 cubed if we wanted, or we could just leave it in the 3/2 power, either way. And then this would be minus 2/3 times the antiderivative of this. And again, we could use the power. So this would turn into 5/2, and we would have to drop the reciprocal 2/5. And then 2/5 times 2/3 should be 4/15. So we'd end up with 4/15 x plus 3 to the 5/2 power, which again, we could write that as x plus 3 to the 5th power and the square root of all that if we preferred, plus c. And this would leave us with our final antiderivative. Fairly gross, I would say, but when taking antiderivatives of products of things, it's naturally what's going to happen, because we're trying to piece together something that would be the result of a power rule, and often we're going to have multiple terms, or sorry, not power rule, I meant product rule, but we'll piece together lots of terms that will, when differentiate, leave us with something so simple. In the next video, we will look at what happens when it's a definite integral. And the short answer is it works just the same as any other. We take a general antiderivative, and once we finish solving the antiderivative, we plug in the boundaries of integration. So since the first part, reading this as, reading this formula as, if we were to put it in u and v form, we'd have antiderivative ab of u dv is equal to uv minus integral v du. And essentially, we just need to plug in a and b into that first component because, as I said in class, that part is kind of like it's already been integrated. And then the second part, we still need to finish the integral for. So what I would suggest doing is just finishing the antiderivative and then plugging in the boundaries afterwards. But we'll look at that example in the next video.